Okay, here we go. We are going to be talking about radioactivity in nuclear processes. I like this, Calvin and Hobbes. Here's a little town. Here's a steam shovel scooping out a giant hole. Here comes a bulldozer pushing thousands of barrels of toxic nuclear waste in the giant hole. Over the years, the dangerous poisons seep into the underground waterways. The cancer rate of the nearby town triples. If you want me, I'll be under my bed. So that's what most people think of when they think of nuclear. Let's enlighten you. That can happen, but we, yeah, anyway. Hold on, you can't be in here. This suit's power cord, it's radioactive. So today you need to be making sure you're working on Chapter 10, Learn Smarts, and Homework 10A and 10S. This is one of 2 days only that we're spending on nuclear. So you've got to get them done because on the third day we're taking the test. So we're going to talk about nuclear vocabulary today, symbols, equations, half-lives, and intensity. We're going to do a nuclear decay activity. That is in your notes. So let's go ahead and get started. I'm going to tell you about a case study because this is a medical thing and you need to make sure that you are understanding with case studies. This is my sister-in-law, Tamara Lynn DeMille Frost. She was born on June 11th, 1970, to Jim D. and Lynette Bigelow DeMille. She was called home on Thursday, November 13th, 2003, after a long, hard fight with cancer. First thyroid cancer, and then leukemia. So your thyroid is like a butterfly that's around your esophagus, and here's the different stages of thyroid cancer, and they say you can feel lumps on your thyroid there. So if you can feel a lump coming right there, that's what thyroid cancer is. It's the fifth most common cancer in women, and nearly 2 out of 3 cases are found in people younger than 55, and Tammy was younger than 55. About 2% of them occur in children and teens. The number of deaths due to thyroid cancer this year was 0.5 per 100,000, which Tammy was one of them. What they do to treat it is they use a seed crystal and they put it in the thyroid cancer, and they basically use radiation to heat it up to kill the cancer. That can be good or bad. For her, it ended up causing her to have leukemia later. So let's talk about what a radioactive nuclei is. A radioactive nuclei, the main three things that we talk about with radioactivity are beta rays, gamma rays, and alpha rays. Alpha rays are positive, beta rays are negative, so that you can see that they attract to the opposite plate, and gamma rays have no charge. So an alpha ray has a positive 2 charge. It's a helium nucleus. Electrons have a negative charge, which is the beta rays, and gamma rays have no charge. So what things can stop them? Alpha can be stopped with paper. Beta gets stopped by skin. Medical x-rays can actually be stopped by cement. That's why they always go hide behind the wall. Gamma rays, you need 5 feet of concrete to stop them, and neutrons will even go through 5 feet of concrete, so they're very, very intense. If you have thick lead, like 0.5 centimeters of lead, like you put on in the aprons when you're in the dentist chair, that will stop gamma also. So, what is a radioactive nuclei? It's a nuclei that undergoes spontaneous change and emits energy in the form of radiation. It emits some kind of particle and energy. Radioactive decay is a process in which an unstable nucleus changes energy states and produces, in the process, emits radiation. And then a radioisotope is an isotope of an element that emits the nuclear radiation. So these are some definitions that you need to know. Basically the same kind of thing going on with all of them. If it's radioactive, it's an unstable nucleus, it's going to decay. It's a radioisotope of some element on the periodic table. So let's talk about each one of these. So alpha particle is identical to a helium nucleus. So it's lost its 2 electrons in its outer shell. It's 2 protons and 2 neutrons. That's it. A beta particle is identical to an electron, but is produced when a neutron changes into a proton and an electron. And then the gamma ray is a high energy ray that is like an X-ray, but with even higher energy than an X-ray. Okay, so over here on the side here, you can see this is an alpha, this is a beta, and a beta positive. We'll talk about that in a minute, and a gamma. Right, if you need the subjects pause it at any time, go ahead and have them pause it or back up. I'm just going to keep going, so if you need more time, let them know. All right, so again, alpha, beta, and gamma, those are not the only ones. You can also have a positron. This is the one in the purple down here. Positron is a positive electron, also known as antimatter electron. If you watch Star Trek, Data has a positronic brain, so instead of working on electrons, he works on positrons. Is just the charge of the electron is opposite. Gamma has no mass, no charge. Alpha has a positive 2 charge and a mass of 4. Other things that you might want to know is a neutron is a 0, 1, 0. And these nuclear symbols you should be familiar with. We've been using them, so hopefully they're not something new. So equations for nuclear reactions, really easy. You need to have a radioisotope, an isotope of an element that will emit nuclear radiation. So just a real quick review of nuclear isotope symbols. The top number is the mass number. That is the number of protons and the number of neutrons added together. The bottom number is the atomic number. They don't have to give you the bottom number if they've given you the element symbol, because you can look it up on the periodic table. Okay, you subtract the mass number from the atomic, take the mass number minus the atomic number to get the number of neutrons. There are 3 different isotopes of hydrogen, and it's one of the only isotopes that has specific names for each one. So 1 is protium, 2 is deuterium, 3 is tritium. Sort of unique. But we can do any element on the periodic table and any of its isotopes this way. Okay, so we need to be able to write the following isotopes. So let's go ahead, and for this first one, iodine, you would write your capital I, you would put your 131 up at the top, and then iodine is number 53, so you would put it at the bottom. A beta particle can be written 2 different ways. You can use the beta symbol with a 0, -1, or you can do an E with a 0, -1. So either one is accepted on that one. If we were to do uranium over here, we would put the 238 at the top, put our capital U, and uranium is 92. All right, so that's basic stuff that you need to know to write isotopes. Now, this is where the nuclear equations come in. They are so easy. The top numbers have to add to the top numbers on the other side. So the arrow becomes like an equal sign. The bottom numbers on the one side have to add up to the bottom numbers on the other side. So here we have 196 and 0. So we're going to have 196 on the top. We have 82 minus 1, so we have 81 on the bottom. 81 tells us the symbol. If we look on the periodic table, it should be TL. Let's uncover it and see. We got it. Okay, would you do the other 3 real quickly? Pause the video and then come back and see if you got them right. Okay, I'm going to show you the answers. See how fast you were. See if you were able to do that. Oh, we got to be careful though. I bet some of you got thrown off. Remember that this is an equal over here and over here. So when we were doing it, we needed to make sure that one side added up to the other. So if you messed up on that, be careful. All right, so nuclear decay, we call it, we have a parent and we have daughters. Sorry, no sons. So the parent atom is the radioactive atom, and it will give off energy and a particle and become a daughter product. And then the daughter product could give off a particle and become another daughter product. And so you just keep getting daughters and daughters and daughters. And they can go until you finally end up with a stable element. or isotope. Okay, a positron, we talked about it just a little bit ago. A positron is basically an anti-electron or an opposite electron, an antiparticle, or an antimatter counterpart of an electron. The positron has an electric charge of +1 e and a spin of a half. It's the same mass as an electron, so it's just got the opposite spin. Electron capture just means I'm capturing an electron, or a beta, which is a 0, -1, or a 0, -1 e. That's what a electron capture is, just putting that beta on the reactant side. Okay, here's another one where we do an electron capture. Let's see how well you do on this. Again, pause the video for a minute, or 30 seconds. It shouldn't take you very long. Remember, the bottom number is the identifier of the element. Top number is just the mass number, but the arrow sign is the equal. Okay, coming back, let's see how you did. Now, whenever you have electron capture, and I forgot to tell you this, you're going to end up with a gamma particle. So it's just extra energy given off. All right, it's moving forward. So you should be able to take and write a formula for these things. Now, if it says emission, it goes on the product side. If it says capture, it goes on the reactant side. If it says decay, it goes on the product side. So sort of listen to what the words are that they're giving you so you know which side it goes on. Bombard would be on the reactant side. Okay, so I'm going to give you a few minutes. I'll show you the first one so you sort of see what's going on. So we have iodine 122, and it's going to give a positron emission. So we're going to have iodine on the reactant side, arrow, positron emission, plus whatever else is needed to add up to the 122.53. So we're going to end up with this. Okay, would you do the other three? And again, for this right here, you could have written 0, 1, e. And sometimes they do 0, 1 with a fancy P for positron. Okay, coming back, let's go ahead and see how you did. Check your answers. Again, pause the video if you need to see it a little bit longer. I will be posting this online. It'll probably be already posted by the time you see it, so make sure that if you need to go back over it, you can. All right, so your turn again. Let's see how you do. Some more here to practice. Again, pause the video. Coming back, let's see how you did. The first one, the second one, the third one, and the fourth one. Okay, again, pause the video if you need to look at these a little bit more in depth. Again, though, they will be up online if you need to look at it a little bit more. Okay, so the next thing we need to talk about is isotope half-life. An isotope half-life is basically what it says. Half of it is gone. So how long does it take for half of it to be gone? So if you look at this is where I start, and when half of it is decayed, that's where it is. When another half is decayed, this is where it is. When another half is decayed, that's how much it is. So the gray ones would represent the daughters, and the parent would still be in the red. And you end up getting a curve like this. Okay, so half of a half of a half of a half, keep going down. So here's another way to look at it. Each half-life is different for every isotope. Some isotopes go very, very quick and even are not very long, a couple seconds. Some are years, some are millions or trillions of years. So depending on the half-life, depends on how long it sticks around and how fast this half-life is, how fast the rate of decay is. So there is a formula that you can use if you're given an initial amount to figure out how long something will take and how much you have of something. So A0 is the initial amount that you have, A is the final amount, and then you've got the half-life and the time. Now, the half-life is also known as T1/2. So most often you'll see it written as T1/2 instead of the H, and time is usually a capital T. So this equation is nice, but usually it's written like this instead, the capital T divided by T1/2, more like over here. Now these two equations are really nice because if you need to find time, then and you can find one of these other things that you need, for instance n or whatever, you can plug in and get what you need. You can rearrange this equation right here, so it is 2 to the n power is equal to a over a0 over a, and then once you've got that number, then you can take log of both sides and get what n is. So log of 2 times n is equal to log of whatever this is. So it makes it really easy and fast to do. Most of the time though, you can just look at it and say, oh, that's 2 half-lives or 4 half-lives or 6 half-lives or whatever, because you know 2 to whatever power is equal to 6, or 2 whatever power is equal to 8 or whatever. Very seldom do you have the point whatever, but in real life you do have the point whatever. You don't have you don't usually get an exact half-life. Okay, so here's the decay of carbon-14. Carbon-14 we use a lot in archaeology to do dating of stuff, how old stuff is. One half-life of carbon-14 is 5,730 years. So if we take something living next to something that's dead, we can see how much carbon-14 at that area it would have, and then see how much the dead thing that used to be living has, and we can figure out how much it had, how long it's been. So some examples here. We have rubidium-79 decays by positron emission and forms krypton-79, which is a gas. A weighed 100 milligram sample of solid rubidium was allowed to decay for this many minutes. So this is time, this is A0, and weighed again. Its mass was, here's the A final. What is the half-life? So I'm looking for T1/2. Okay, so the first thing we want to do is say, all right, I have, I know that N is equal to, or the number of half-lives is equal to T divided by T1/2. I also know that ln of 2, let's not do that. Let's do, I know that, let's go back a couple pages because I'm forgetting the equation. Okay, so A is equal to A0 divided by 2N. And since we have A0 divided by 2N, I'm going to rearrange the equation so it's 2N is equal to A0 divided by A. And then we're going to plug in. I have got 25 milligrams, whoops, and 100 milligrams. So I'm going to take 100 divided by that. So 2N is equal to 4. Well, then I know what N is because N has to be 2. That was a simple one. So then I come back to here and I'm looking for the half-life. So I'm looking for this. So I'm going to go T1/2 is equal to total time divided by N. So we take total time, which is 42 minutes, divided by 2 gives me 21 minutes, and that would be my answer. All right, I'm going to change this up a little bit because I'm having a hard time writing. You probably can tell by my writing there. So the next one, decays the positron emission, blah, blah, blah. It has a half-life of this. So we've got T1/2 is equal to 7.7 minutes. How long, so I'm looking for T total, will it take for this much AO, 200.0 milligrams, to be reduced to A, 25.00 milligrams? Okay, so this time we're going to look for T. So if we take this equation up here that we had and solve it for T, T is equal to N times T1/2. We don't know what n is yet, so we're going to look at A equals A0 divided by 2 to the n. So 2 to the n is equal to A0 divided by A, which is equal to 200 divided by 25, which is 8. So 2n is equal to 8. Well, that's 2 times 2 is 4 times 2 is 8, so n equals 3. Usually on the problems they do it pretty simple for you so you can figure it out. Haven't even used a calculator yet. So then what we're going to do is time is equal to 3 times 7.7 minutes. And now I'm going to use my calculator because I don't want to mess up. 7.7 times 3, 23.1 minutes equals 23.1 minute. And that's our answer. Okay, going forward. Suppose you gave an initial reading of 120 units of activity, so this is AO, and it took 35 minutes for the reading to drop, that's T, for the reading to drop to 60 units. What would the half-life be? Well, to go from 120 to 60, that's half of it, so the half-life is 35 minutes. That was easy, I just had to read it. The activity of the radioactive substance is measured at 9 a.m. Okay, 9 a.m. At 5 p.m., the activity is found to be 1/16 of the original value. So the original value must have equaled 1. So I've got A equals 1, O equals 1, A equals 1/16. Okay, so then 9 a.m. So 9, 10, 11, 12, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 hours is my total time. And I'm looking for T1/2. All right, so if I set this up, A is equal to AO divided by 2 to the n, so 2 to the n is equal to AO divided by A, which equals 1 divided by 1/16, which equals 16, is equal to 2 to the n. So if 2 to the n, when n was 3, is 8. So 2 times 2 is 4, times 2 is 8, times 2 is 16, so n is equal to 4. Then we're going to plug that into the equation. Total time is equal to, oh, my brain is not working this afternoon. There it is. Total time is equal to n times T1/2 times T1/2. So we're looking for T1/2, so we're going to take T1/2 is equal to the total divided by n. The total time was 9 hours. And we're going to divide it by 4. So we're not going to be perfect here. So I'm going to take my calculator and go 9 divided by 4. And I get 2.25 hours. And if they wanted it in minutes, I'd times it by 60. And that's 135 minutes. So I could do OR. Okay, that's my T1/2. Okay, so the health effects of radiation. There's lots of things that are going on with radiation. So eyes. High doses can trigger cataracts, there we go, months later. Thyroid, this is a big problem. This is the problem that Tammy had. If you have too much radiation, it can cause radioactive iodine to build up in the thyroid. Mostly children are at risk, but it can cause leukemia. Lungs become damaged, and it's hard to breathe in when you're breathing radioactive stuff. Stomach is vulnerable if the radioactive stuff is swallowed. Reproductive organs causes sterility. Can't have kids. Skin, high doses can cause redness and burning and lesions and all kinds of nasty stuff. And bone marrow, it can actually kill it. If you look here, radiation can lead to leukemia and other inhumane things. So if they don't do, if they're trying to kill one cancer, they can actually cause leukemia. And that's what happened with my sister-in-law. So over here it sort of tells you what you need to worry about as far as dosages. And if you'd like to come back to this, you can. I'm going to go ahead and go forward. Remember the penetrating power of radiation. Gamma rays are the most penetrative. It takes 10 centimeters of lead or 5 feet of concrete to stop gamma rays. Beta radiation can be stopped by 0.5 centimeters of lead. That is your dental apron. And alpha particles just by paper. Very easy to stop. Okay. Going forward. Oh, by the way, X-ray medical can be stopped by thin lead. So you often do lead in the windows there so they can see you, but it stops it. Gamma rays take thicker lead. Okay, so radiation's effect on health are being investigated at the molecular level, but basically if something is exposed to radiation, a cell's exposed to radiation, its DNA might be damaged. If the cell with damaged DNA can either die or attempt to repair itself. If it attempts to repair itself, then we sometimes get misrepair right here, and we end up with a cancer cell. If it repairs and does fine, then we end up with a normal cell. So if there's not much damage, usually we end up with just normal cells and it's fine. If we end up with cell death, then we have a problem if it's a widespread kind of thing. So you can sort of read what's going on here. But that's what's going on at the molecular level. Whoops, I went the wrong way. Sorry. Fat fingers. All right, so let's go ahead and listen to this.
Our body is made of billions of cells, which are arranged to form organs. Approximately 1.5 meters of DNA are stored in each cell. DNA is a giant molecule formed by 2 complementary strands which are wound into a double helix. The hereditary message is chemically coded along the DNA molecules. There are 4 different elements which make up the code and which are referred to as bases. Their sequence determines our genetic heritage. These bases combine to form an amino acid. Proteins are all amino acid chains. The DNA sequences contain genetic information, which are referred to as genes, and which carry the manufacturing drawing for all the proteins of a cell. DNA undergoes permanent attacks, and there are numerous aggressive agents. The following could be mentioned: solvents and pesticides, combustion smoke, viral aggressions, ultraviolet radiation, and ionizing radiation. All molecules can be affected by radiation, but it is when DNA is impacted that there are the greatest consequences for cellular operations. The action of ionizing radiation on DNA may be direct, as well as indirect, via the water contained inside the cells. Water consists of free radicals. These free radicals, which are chemically very reactive, damage the DNA molecules located nearby. DNA damage induced by radiation varies according to the nature of the radiation and the level of exposure. Luckily, the cell has been provided with extremely efficient repair systems. So, there is a repair system which starts operating when DNA is damaged. In most cases, the repair works, but sometimes errors in the genetic code persist. These are referred to as mutations. The future of a badly repaired cell is uncertain. It can be identified and eliminated by the immune system, or survive without any consequences for the body. However, both cases can affect our health, when cells die in great numbers, or when they are transformed into cancerous cells. If the radiation dose is high, a significant number of cells will be damaged and will die. This will involve effects which are referred to as deterministic effects. High doses generate systematic effects on the people who have been exposed. Their severity depends on the dose of exposure, on the size of the body area which has been exposed, and on the type of organs which have been affected. The occurrence of cancerous cells is the other serious consequence. However, as opposed to deterministic effects, this effect does not systematically affect each person who has been exposed. The development of a cancer cannot be predicted at the scale of an individual. Only the risk of occurrence in an individual can be estimated. Such effects are referred to as stochastic effects.
Several groups of studies have shown that there is an increased risk of cancer in populations exposed to high doses, and that, in some cases, it may take several decades before the cancer appears. The following are 4 cases. In the 1930s, female workers in the clock-making industry used radium-based paint to paint the hands of the clocks and the numbers on the alarm clock dials. In the 1950s, before the mines were ventilated, uranium miners used to inhale air which was highly contaminated with radon. Thereafter, the levels of exposure dropped systematically. The bombs of Hiroshima and Nagasaki in August 1945 caused the immediate death of 200,000 people. The 300,000 survivors were irradiated with various doses, which were all delivered at a high rate. For more than 30 years, the survival rate for cancer patients has steadily increased as progress has been made in the medical field. But secondary cancer caused by treatment is still a risk. Despite efforts to target only cancerous cells during radiation treatment, the rays still touch the healthy surrounding tissue and may have carcinogenic effects. These last 3 groups of studies have made it possible to quantify the relationship between radiation doses and cancer frequency. But it is difficult to assess the validity of this cause and effect relationship when the results are extrapolated for current doses, which are much lower. In order to determine if these extrapolations are accurate, studies are also conducted on low doses and dose rates. As there is no scientific evidence, a careful attitude involves considering that effects exist at low doses. As regards radiation protection, actions are conducted on the basis of this principle of precaution.
Okay, so let's go ahead and go forward here. We need to worry about the inverse square law, and the inverse square law basically says the farther you are away, the less exposure you're going to get. It's all about the distance. So the intensity of the radiation is equal to the distance squared, basically, proportional, inversely proportional. So that's why they move away from you when they're taking an X-ray, so they have less exposure. So the intensity of radiation is 18.5 units at a distance of 50 centimeters. So I1, D1, what is the intensity, I2, at a distance of D2? So plugging into the equation I1, let's make sure I've got them, I think they're both on the top. Nope, they flip. Okay, so I1 divided by I2 is equal to D2 squared divided by D1 squared. All right, so plugging in what we have, we want to solve for I2. So I'm just going to rearrange it real quickly and then plug in. So I2 is going to be equal to I1 times D1 squared divided by D2 squared. So plugging in 18.5 times D1, distance 1, which is 50, and I'd square that, divided by 100, and I would square that. So let's plug it in our calculators and see what you get. Everybody do it with me. Might be a little slower here. 18.5 times parentheses 50. I think I've got a button that's just 15 squared. Okay, and then I'm going to bring that arrow down, parentheses, and then divide it by parentheses. Whoops, that was the minus sign. Divide it by parentheses 100 squared, close parentheses, enter, and I get the intensity at basically double the distance, drops to 4.625, so about 4.6 units, which is a big deal if you're half the distance away. Okay, going forward. A radiologist found that in 30-minute period, a dose of radioactive source was this, at a distance of this. What would be the dose at the same amount of time, so I can ignore the time, at a distance of 2 meters from the source? So again, I1 divided by I2 equals D2 squared divided by D1 squared. And this time we are looking for the dose I2 again. So I2 is equal to I1 times D1 squared divided by D2 squared. So I1 D1 D2. So 75 times 12 squared divided by 2 squared equals, so that's 75 times 144 divided by 4. So plugging that in, I got way too much. What's going on? Oh, what did I do? Because that's not right. I1, D1, D2. Did I rearrange this wrong? D2. think it's supposed to be opposite. I think it should have be. Go back here just a second, sorry. D2 squared. Oh, nope, what I got was right. It's just that we're getting closer, so it's going a lot higher. I was freaking out for a minute because I was thinking we were backing away, but we're not. So 75 times 144 equals, divided by 4. So you have at I2, at that closer distance, 2,700 units. So we had it set up right. I just was a little confused because it's really large. Okay, let's go forward. Oh, and I already had it in there for you, so isn't that nice? All right, so measuring radiation's effect. In a typical year, most people, all sources, will get about 360 millirems. You can get radiation from dental x-rays, chest x-rays, flying to DC, to Los Angeles, living outside a nuclear power plant for a year. Everybody thinks you're going to get a lot, but like 0.1. Smoking other things that can cause a health risk. Radioactivity cannot be detected by your senses, yet it can have a very powerful effect. Nuclear radiation will damage or kill rapidly dividing cells such as bone marrow, skin, and the reproductive and intestinal systems. Cancer cells divide rapidly as well, making radiation an effective treatment for cancer. Food is irradiated to expose by exposing it to gamma radiation to kill any living organism in the food, so the food lasts longer. Afterward, the food is not radioactive. A lot of people think, oh, it's so horrible. It just killed the bugs on it and has a considerably longer shelf life, so we can keep milk outside the fridge on a shelf. Okay, so measurement of units for radiation. We've got several physical units that we need to worry about. A physical unit of radiation is a radiation measurement unit that indication of the activity of the source of radiation. For example, the number of nuclear decays per minute. A biological unit of radiation is a radiation measurement of the unit indicating the damage caused by the radiation in living tissue. So a Curie there's several different units, either physical or biological. And we're going to talk about the physical first, then the biological. So a Curie is a physical unit, and it's a unit of radiation measuring corresponding to 3.7 times 10 to the minus 1 nuclear disintegrations per second. So that's a lot for comparatively. Becquerel is a physical unit which says basically you have 1 disintegration per second. Okay. All right, so these are the biological ones. A roentgen is a biological unit of radiation measurement used with X-ray and gamma rays. So the quantity of radiation that generates 2.1 times 10 to the 9 ions per centimeter cubed of dry air, or 1.8 times 10 to the 22nd ion pairs per 1 gram of tissue. A rad is a biological unit of radiation measurement corresponding to the transfer of 1 times 10 to the minus 2 joules, or 2.4 times 10 to the minus 3 calories of energy to a kilogram of tissue. A gray is a biological unit of radiation measurement corresponding to the transfer of 1 joule of energy to 1 kilogram. So you can see they're getting more and more. Okay, a rem is a biological unit of radiation measurement corresponding to the health effect produced by 1 roentgen of gamma rays or X-rays, regardless of the type of radiation that was involved. So a rem tells you how much damage is going to be caused. Okay. Okay, the average dose of radiation per year for a person is about 0.27 rams. Generally, no detectable biological effects are noticed for a radiation dose less than 25 rem. A single dose of 25 to 100 rem can cause a temporary decrease in a white blood cell count. A dose of more than 100 rem causes radiation sickness, which is vomiting, nausea, fatigue, etc. And LD50, that's a lethal dose. So the lethal dose that kills 50% of the population is 500 rem in humans, while 600 rem is fatal for the entire population. Okay, so as we're looking at this, film badges are often required for people that are working around radioactivity so they can measure how much personal exposure that they've had in rems or sieverts. The activity of a radioactive source is measured in becquerels or curies. So this is, remember, we're talking about physical versus biological, depending on what units we use. So the intensity of the gamma source is measured in roentgens. Absorbed dose in rads or grays, converted to dose equivalents in rems or sieverts. So we're going to do a radioactive decay activity. Now what you're going to do is we're going to do a nuclear decay activity with M&Ms and Skittles. Pencils, plate, or paper towel. You'll need 2 cups, one empty and one full, with either M&Ms or Skittles. It's fairly easy. You're going to dump the M&Ms or Skittles onto a paper towel. Count how many you have. Then the ones that are M or S up, leave and count them. So you can either count them and put them into a cup, or count, I would probably do it that way. I would count the M or S that are up and put them into a cup. You're going to write that down. So you're going to write as your 0 trial how many total you have, and then for your trial 1, how many were M or S up. Then you're going to scoop the ones that were M or S down into another cup and just sort of set it aside. You'll dump out the cup that had the ones that were M or S up. Again, count how many are M or S up, put them back in the cup, put the others back in the cup with the others that were discarded before. Keep doing that until you have none that are left M or S up. Then start all over again. Do the trial 3 times, put it on a graph where you're putting that each trial on as a different color, and see how closely each of them fall to each other. Okay, so when you're done with that, you can eat the M&Ms or Skittles, whichever you chose to do. Make sure you clean up, put all the other stuff in the garbage. I do not want the cups back. Once they're out, we just want to throw them away. So share with your friends, be happy, whatever. Make sure you're working on your Learn Smarts, your homework 10A and 10S, and make sure that you finish the nuclear decay activity so you can sort of see how this works. And we'll see you in class next time. Remember that you only have one more day of nuclear, and then we have the test. There really is no time for review. I will be giving you the review next time, but they sort of go really quick, because otherwise we'd have to have the test right as you came back from spring break, and that would not be good. Okay, I'll see you in class. Okay.